everybody to our Rutronik webinar series, Rutronik Connects. Rutronik Connects is a 4 weeks webinar series we are hosting together with our suppliers. For this week, we will focus on ultra-wideband, LoRa, and other wireless technologies. In addition, we have some partners on board for add-ons like machine learning, energy harvesting, and cybersecurity. This webinar introduces ultra-wideband together with our supplier Inside SIP. We will explain what it is, what its unique characteristics are, and what kind of use cases it is suitable for. So, my name is Heike Kubisch, and I'm a corporate product manager within the wireless department of Rutronik. Today, I would like to welcome Nick Wood from Inside SIP, our long-term partner for wireless modules. Before we start, some practicalities. The duration will be 1 hour of our webinar today. Questions can be typed on the right sidebar, and we will answer them at the end of our presentation. Don't hesitate to ask questions. We are encouraged if you ask them. In addition, the presentation will be recorded, and afterwards you will receive the slides from us. So, hi Nick from Inside SIP.
Hello, switching my stuff on. Hi.
Hi, hello. Oh, you can go
on. Right, you want me to bring up my presentation then?
Yes.
Right.
Now it looks good.
That looks better, yep. Okay.
Yep.
So, ultra-wideband technology, what it is and what you can do with it essentially is going to be the main focus of the presentation. So if I just move on quickly to the agenda. What is ultra-wideband? It's probably not as well known as some other technologies like Wi-Fi and Bluetooth and so on. So I'm going to talk about what it is and why it's good at what it does. I'm then going to talk about using it for position measurement, which is its key use case, I would say, the one it's certainly gaining traction for now. And compare it a little bit with other alternatives that you might have heard of or be aware of, and then look at some different ways of using it. I'm then going to talk about how you use it together with Bluetooth Low Energy to make more effective solutions, and then briefly mention there are some other applications. And at the end, I will be just talking about what we have to offer for ultra-wideband. So that's the agenda. So I'm going to start off with a very short lesson in physics and engineering, just to explain what ultra-wideband is, and particularly what this phrase wideband, what that means, and what the implications of it are, because I guess some people may not be aware. So we'll start with a very basic question: what we mean by bandwidth. This is a term you hear talked about a lot in RF, but what does it really mean? Well, if you compare the two waveforms on this graphic, the blue one is a pure sine wave, so at some frequency, it doesn't matter what frequency. But if you have a pure sine wave, this is a zero bandwidth signal. You know, if it's just a pure sine wave, it's just one frequency, and bandwidth basically means the range of frequencies contained within a signal. So a pure sine wave has no real information carrying capability, because you can receive a signal, but you can't really do anything with it, because you encode information on RF signals by modulating in one way or another the signal. So you can't do any timing with it, because it's just a continually oscillating signal. You can't carry any data with it. So that's zero bandwidth. Then the red one is the opposite of that. That's just a what we might call a delta pulse. It's a very theoretical thing, but it's basically a pulse that exists in one moment in time. And from a technical perspective, anybody who's done maths and engineering or physics and has studied Fourier transforms, you'll know that this is a combination of every possible frequency in the electromagnetic spectrum, all put together to make this one pulse. And with this sort of pulse that takes, zero time in this theoretical case, you can carry an infinite amount of information in theory, because you can have any number of these pulses on or off over a particular time period. So it has a very high information carrying capability. And it also has a precise timing capability. So because it exists in one point in time, you detect the signal and you can time exactly, in theory, of course, when it arrives. So that's what bandwidth means when people talk about RF. It's the range of frequencies contained within a signal, because you need a range of frequencies to actually carry in information. And then it's what width of how wide that range of frequencies is. So that's all theory. In practice, of course, you can't have infinite bandwidth. So what is UWB? Well, it is, compared with most other types of communication, it's a very wide set of frequencies. At low power in terms of the power per frequency, but they're all, you're covering this wide range of frequencies. So what are the implications of that? Well, it can exist pretty well with other protocols, because you detect the signal by seeing, movement effectively in a wide range of frequencies, which is distinct from, say, another type of radio transmitting in a narrow range of frequencies. You can tell the difference. And like I said, going back to the theoretical examples, you can carry a lot of information in it. So what can you use it for? Well, you can use it for high data rate transmissions. There's reasons perhaps why that route hasn't really taken off. Or you can have it for very short, sharp pulses, which you can use for timing. And that's where the focus is today. So back in the real world, what does this mean? Well, in the real world, devices tend to operate on basically two channels that have been selected, 6.5 gigahertz and 8 gigahertz with a 500 megahertz bandwidth. Now, maybe those numbers don't mean much to you, but if to compare it with, say, Bluetooth has multiple channels, but each channel is only 2 megahertz of bandwidth. So you can see ultra wideband has a much larger bandwidth. Wi-Fi operates on there's a number of different options, but between 20 and possibly 80 megahertz typically. So you have this very wide bandwidth with ultra wideband, and what this allows you is precise timing. Essentially, you can have these short, sharp pulses that you can localize in time. Now, looking at this again, looking at these signal diagrams, this has some practical benefits, because if you look at this ultra wideband and you've got some noise, because you don't just get a nice pure signal like my theoretical graphs, you get one with noise, and then you see this short, sharp peak, which you can pick out the time pretty accurately. With a narrow band, you don't get this short peak, you get a sort of up and down, and with the noise, it becomes much less well defined in time. An even bigger problem with narrow band is reflections. So with an ultra wideband, you see the pulse, and then you might see a reflection, but the pulse is sufficiently sharp that you can distinguish quite easily between the original and the reflected pulse. What you see with the narrowband signal like this one is a bit of a mess, to be frankly, because you see the outward signal, and then the reflected one is kind of mixed in with it, and you end up with a composite of the two, and so this messes up your any timing consideration. So what you have is these pulses that are precise, and they're quite insensitive to the background noise. So these are the big advantages of the ultra-wideband technology, and it's quite basic physics. It's not because someone's been super clever designing the chip, although you have to be pretty clever to design these chips, but it is due to some basic physics of the type of signal. So, as I said, this is used for positioning. So there's two basic ways of positioning. So the first one is what we call a simple measurement of time of flight. So you send a pulse from one thing to another, so from a tag to an anchor, and then back to the tag. And by timing very precisely and knowing the time in your devices for the pulse to be sent out and sent back, you can have, using knowledge of the speed of light, you get a distance, and you get that quite precisely. So the terms anchor and tag are used quite often in positioning systems. So generally the idea is the anchor is something that's fixed in a particular point in space, maybe something attached to a wall or attached to a large object like a vehicle maybe, and the tag is something that moves around that you want to find the position of. So two-way ranging is pretty simple. It's fairly easy to set up. The problem with it is that you need, it's okay if you're just trying to find the linear distance between two things, but if you want to locate something, say in 3D space, you have to do a lot of exchanges to locate the object. The other method is called time difference of arrival, and here you have a tag and some anchors in it around it, and this tag sends out a pulse. It's detected by all these anchors, and you measure the time that it arrives at each anchor, and from that you can do some maths and work out where the tag is. So the complexity here is that, so I'm moving on to, what's the difference between these things. The difficulty here is that you're talking about picosecond timing here, so you need to have these anchors very well coordinated to detect these subtle time differences. So yeah, two-way ranging, it's very simple to set up. The software comes with the devices pretty much, and it comes almost working out the box. You can triangulate a tag if you have lots of exchanges with lots of anchors. But as I mentioned before, you have to do many more exchanges with different anchors if you want to locate an object. So if you've got lots and lots of objects you're trying to follow at the same time, you're going to have much more risk of things interfering with each other. You can have much higher power consumption, and yeah, you need to identify all the anchors to communicate with. Time difference of arrival, by contrast, is just one tag that can just do what you call a blink. Basically, it's just pulses, and then the anchors just pick up the signal and work out where it is. But you need a quite complex system behind that to reassemble the signals from the different tags, put them together, and yeah, calibrate them to this high level of accuracy to make it work. You can also do angle of arrival with the UWB, so you can do this with current ranges of devices, and it has some advantages over the Bluetooth Low Energy version of this because it's operating at a shorter wavelength. It means your device can be smaller. You don't need such a big device. You don't have such big problems with reflections for the reasons I said earlier. So you can do very quickly a sort of 2D position, or if you know objects are on a floor, then you can perhaps localize pretty accurately with one device. And typically UWB devices just need 2 antennas. So you can also use angular arrival with this technology as well. Another big advantage of UWB is the way that it can be used for secure entry. So traditional keyless entry systems via what I've labeled RSSI, which basically means the signal strength. Fundamentally, it's the strength of a signal. So old-fashioned ones just detected the proximity of a signal and use this to open a car in a sort of keyless entry system. People say keyless entry. It's a bit of a funny phrase, really, because it isn't keyless entry. It's contactless entry, really, but people say keyless entry, so I'll use the phrase. So the trouble with this subject is it is very vulnerable to what's called a relay attack. What this means is that you have your key that's transmitting a signal, and you have your car that's listening for a signal. But what you can do is boost that signal from the key and then send it out, and so the car thinks that the key is much nearer than it really is. This is quite easy to do with a signal strength system. It doesn't require any sophisticated cryptography or anything like that. So, and this is a real world problem that, you've had cases where, say someone's left their car key on a table in the hall just by the front door. People pick up that signal and give it a massive boost with a transmitter and send it to the car, and there you go, the car's open. And you don't need to worry about any sort of cryptography between the key and the car, because you just transmit that sort of transparently. But there's no timing in that, so you can then open the car a long way away from the key. With the two-way ranging with UWB, this is a time of flight solution, so this simple hack no longer works. If you put this relay in the middle, it just simply will add time to the exchange, and it will be detected. So you will see quite clearly that the key is not close to the car, as it seems with the RSSI solution, but is in fact quite a long way away. And this is, it's a real problem. It's not a theoretical problem, and the cars have been stolen using this relay attack, and the UWB is a much more secure solution. I won't say it's unbreakable, because very few things are, but it's orders of magnitude harder to hack. So pairing UWB with other positioning methods, what have you got? Well, Bluetooth beacons, they work up to a point, but they are essentially an RSSI type solution of the type I described in the previous slide. And of course, it's very, when you're detecting a signal strength, there are all sorts of things that can affect that aren't just the distance between the transmitter and the receiver. If you have some obstruction, you have a person in the way, they will absorb a lot of the signal and make it look further away than it is. You can have reflections. You don't know from the start the orientation of the receiver and the transmitter. That can affect the signal strength by quite a lot. So you don't know how powerful your transmitter is necessarily. So all these things affect the accuracy. So you can get a certain level of accuracy, but with the UWB type solution, you're talking about a sort of 10 centimeter level accuracy. You'll never get that really with a beacon solution. So then Bluetooth angle of arrival arrived with a bit of fanfare some years ago. Honestly, it hasn't super well taken off, I would say, and it's very, very sensitive to reflection. So in some environments, it'll work reasonably well, but certainly if you put it anywhere where there's metal around, and that can include anything, including like a suspended floor, which often has metal underneath it, you will suddenly start to see all sorts of issues with that sort of technology. And both of these, the accuracy will degrade with distance. Whereas UWB, the accuracy is down to timing errors, and those don't really change over distance. So it's kind of as accurate at a few meters as 50 meters with UWB, because the error in it is due to a sort of fixed timing error, which doesn't really change with distance. So you might also have heard about channel sounding. So this is quite new. I'm not going to go into the details of this because it's a Bluetooth technology, but essentially the principle is that you send two pulses on different channels, which are different frequencies, and then you measure the phase difference between them. How well will this work? Well, it's a bit early to say. Theoretically, it could certainly do better than the other technologies that have been proposed with Bluetooth, but we haven't seen how well it works in the real world yet, and it does still basically revolve around detecting small difference. It doesn't really seem to get over the reflection issue that well. And people talk about using multiple antennas and different ways of improving it, but it kind of seems complicated, and complicated is rarely good. Maybe with refinement and work, it can work well. I wouldn't like to say. The fact is, we have a spec, but we don't have devices to test as of today. So who knows? So what are people using ultra wideband for? Just a quick talk about standardization. This was until recently quite a barrier in market adoption, because there was a standard that defined certain physical layer aspects, but there wasn't really any standard at the sort of protocol that meant devices could work with one with another. They were all using the same basic, some basic aspects of the radio, but they were largely proprietary. And then things moved on. They just defined more common standards, and then finally there's a FERA consortium that does offer interoperability. So now we do have genuinely interoperable devices, and this is obviously a big step forward. And then there's also specifications on digital keys as well. So the whole thing has moved on. It's also moved on to the phone. So, I mean, this is a list I compiled a few years ago in 2021, and it was on certain high-end devices, mainly from Apple, Google, Samsung, and this sort of enables the phone as a digital key for possibly a tracking tag, or things you could, accessories. And then I looked at the list as of today, and then you can't read it anymore, but it's got a lot longer, and there are a lot more devices. I mean, it is still higher end devices, but it is slowly moving, becoming more and more standard for new devices that move onto the market, and ultimately it could well become a standard feature, and it is already used for things like the Apple AirTag that uses UWB to aid positioning. So what applications do you use it for? Well, the digital key is a big one. Some people are thinking ultimately we won't have physical keys after a while. Everything will be digital. It'll be on the phone. You can use it for asset tracking, people tracking. You want to know where people are in a building. Keep out geofencing. So, if there is a place you shouldn't go, that it could be used to warn if someone's entering somewhere that, if they're wearing a badge, they warn that they shouldn't go in this place. You could put a security tag, so if something starts moving that shouldn't, your suitcase or your bike or something, that suddenly there's an alert goes off to say it's moving out of distance. You can have sort of find me tags that you can use the phone to point around. Digital ticketing is another application. I read recently that there's a project on the Shenzhen Metro to use UWB to do automatic ticketing. It detects, you just walk in and it detects that you're there and tickets you accordingly, apparently. So just talking a bit more about this digital key technology. It's a fast-growing market. You get quite a lot of security benefits because you can make keys individual, so you can detect who's gone in, who's gone out, when they did so. You can distribute a key quite easily. You can do copy control. You can make sure it can't be copied easily, and you can time limit when the key can be used. So say you want to let someone into your apartment to do some work, and you send them a key. They can use it for the day they're meant to be there, but then it expires, so they can't then come 2 weeks later and steal your stuff. So there's plenty of already people using hotel. Say there are hotels where you just turn up and enter without checking in or being given anything. You have the codes or whatever it is. And yeah, you don't have to use UWB for this. You could use other sort of methods, but as I mentioned previously, the UWB does for you a much more secure way of making sure that when you use the key, the person really is there in front of the building, and it's not using some remote access kind of hack. Obviously, with there's this real-time location where you can track objects or people in real time. You can locate valuable assets. People talk about hospitals, for example, where equipment, it doesn't necessarily get stolen, but people don't know where it is. Important equipment that people need to know where it goes. The issue with this, as I mentioned before, is the infrastructure around it is relatively complex, and you do have to end up with quite a complex system to manage and support this. Shouldn't be underestimated that you can just stick up a few anchors and off you go. And then, as we talked about, the geofencing applications, if you have some dangerous thing, if you equip your operators with some sort of badge, you can make sure that they're in the right place, or if they approach a dangerous area or a dangerous piece of equipment, that it switches off when you approach. It also can be used to the fine position of things like, say, vehicle charging, where you need to sort of locate something to use, where you want to sort of have automated charging devices that will just latch on to the vehicle, or wireless charging, for example, that you can guide a vehicle or move a plate so that the charging plate is in the right place to efficiently charge the car. So, slight spoiler alert, we have a product with UWB and BLE together. So why is that interesting? Well, one obvious thing is that if you have a sort of simple tag, UWB tag, that you can configure it nicely with Bluetooth. Obviously, Bluetooth is exactly designed for this sort of thing, so you can set up things like which channel you're using, give the tag an identity, upgrade the application, details of the protocol if there are some variations and so on and so forth. So it's a classic Bluetooth use case where you use the phone to do a simple little application. The next one's not quite as obvious. So one of the disadvantages of UWB is that when the radio is on, it's quite power hungry, consumes a fair bit of current. So if you want a long life, a long battery-based application and with a long life, then it's a bit awkward. So on the plus side, UWB pulses are very short. So although when the radio is on, you consume a lot of current, it only needs to be on for short periods. So one way that you can use tags constructively with BLE and UWB is use the BLE to detect an approximate distance. So BLE is a much lower power technology, so you can have this running all the time, and then when you seem to be close with the BLE, you can switch on your UWB, do some two-way ranging measurements and verify, yep, you really are where the BLE has told you it thinks you are, and then open the door when the secure distance measurement allows. So this allows you to take advantage of the characteristics of but the UWB gives you this accurate and secure measurement. You can also use it in sort of a warehouse example. You know, most of the items in your warehouse are not going to be moving around most of the time, so you don't need to track them all the time. So you could, you know, when you have a particular thing you want to find, you could activate it via BLE, and then once it's activated, you switch on your ultra wideband so you can detect the position of it quite precisely. And then once you've done that, you could then switch it off and return to your default state. So yeah, that's another kind of way you can use the two technologies together to make so you can run things off, you know, small devices, small tags off a coin cell without, you know, burning your battery. So just some other use cases. There are some bit niche, most of them. You can do very high speed data transmission over UWB. You have a high speed data. You know, why don't people use it for this? Well, overall, just Wi-Fi has got a whole industry behind it. That means it's difficult for ultra wideband to compete, and so yeah, it's never really taken off as a technology. It was the Wi-Fi is a huge sort of investment behind it. That's meant it's kind of been the technology of choice. It does have a few cases. So you know, things that require very low latency, it could be used. So things like music, where you're not listening to music, but when you're live playing, those are very, very sensitive to you know, latency issues. So you don't want any kind of latency for that. Or certain kinds of gaming, perhaps you could also, you're quite sensitive to that. So there are some use cases there, and another advantage is it operates in a different part of the wireless spectrum, so you're not then hammered by Wi-Fi or Bluetooth occupying the same space. And then you can also use it for a kind of radar solution. So there are sort of a classic radar where you don't have two devices you're working between, but you send a signal and you pick up reflections, and so you can use it as a radar technology, and it's quite effective in this. And there's the modern chipsets can measure both how far away something is and movement, and you can even use it for quite subtle things like monitoring breathing using this technology. So that's basically my overview of UWB. I will just now briefly introduce our solution, and as I indicated, we have a combined BLE and UWB device. You know, like all of our devices, it's a miniature device. It's got everything inside. So it's got a UWB radio, a Bluetooth radio, the microprocessor integrated with the Bluetooth radio. So it's based on a Nordic NR52833 and a Corvo UWB transceiver. And you just put this on the board with a battery, and it's a UWB tag that also has Bluetooth connectivity, all antennas inside, all ready to go. You literally do not need any other components. Yeah, so basically it's designed as a very complete all-in-one. Put it on the board, don't have to worry about anything. It works. It's Vera compatible, so it does work with suitable mobile phones. So yeah, it's 12 by 12 millimeters, so it's the smallest device on the market. It has a integrated accelerometer, so basically if you want to have a solution where it only starts transmitting once it moves, so which is obviously quite a nice idea because you don't waste power locating a position when it's not going anywhere. So you can have sort of wake up on move functionality. As I said, everything's in there, so you literally just add power to make it a fully functional device. So it's ideal for like a simple tag, for secure entry, for real-time location, asset tracking, a badge or a wristband or something like that. And it's a full set of interfaces that, you know, standard interfaces like SPI, UART, USB, to if you want to integrate it as part of a more complex solution. It has integrated antennas, but if you want to add external antennas, which you might want to do to have some, our antennas are sort of omnidirectional, but you could have a more directive antenna that might be useful in certain scenarios. So in that case, you can attach an external antenna in place of the internal antenna, and have that sort of antenna with some specific characteristics if that's what you want to do. So that's the end of my presentation. I hope it's been interesting and useful to give you some ideas about what UWB is and what you can use it for. Yeah, I'm very happy to take some questions if there are any questions about the technology or anything I've said.
Yes, thank you, Nick. There are some questions, so then I will take hand over. How does ultra wideband compare with Bluetooth distance measurement, like channel sounding or RSSI? Nick? I think there are some problems. We will wait. We will wait for Nick. So I think then I will hand over and we will answer the questions at the end of when Nick is arriving here again into our webinar. So if you still have some open questions, you can find out more information also on our Rutronik webpage, rutronik.com, or on our web shop, Rutronik24, or on our technical engineers community platform, Rutronik Tech. If you are interested in more electronic news, feel free to register for our monthly newsletter or follow us on social media. If you have further questions, don't hesitate to contact me, your local Rutronik sales manager, or use our contact form on rutronik.com. Of course, the presentation slides and the recording will be sent out afterwards. And we do have in this week also other webinars following. So there is one from an ocean with energy harvesting solution, Murata with exploring LoRa, Kyocera with high performance antennas, Edge Impulse with machine learning on Nordic devices, and Yageo Pulse with additional antenna solutions. So feel free also to register for the upcoming webinars within this week. Also,
I think I dropped out or something, but I don't know if there are any other questions or.
Hi, Nick, again.
Yeah, sorry, I don't know what happened there, but were there any other questions?
So the questions we will, I will do this at the end of,
Okay.
I will do some common stuff now, and then we will go on with the questions.
Yeah.
So yes, if you are interested, our next webinar series will be also in the beginning of November with the newest topics about Bluetooth. We will have our suppliers Panasonic, Nordic Semiconductor, Minu, Infineon, Kyocera, and of course again Inside SIP on board, where you can learn more about the latest Bluetooth standard 6.0 and more about our partner solution and the add-ons with antennas. Information about it will be also published on our Rutronik webpage and will be shared within our social media channel. So, yes, Nick, then we will go on with the questions that are missing here. So shortly. So hopefully you hear me again. How does ultra wideband compare with Bluetooth distance measurement?
Okay, I answered that, but I think I must have dropped out or something. But yeah, basically it's more accurate, and that accuracy is not dependent on distance. I'd say would be the key thing, that you have a sort of fixed error, but that error is largely independent of distance, whereas with any of the Bluetooth methods, channel sounding, we don't really know how well it will work, but we'll have to see. The accuracy gets worse with distance. It's more sensitive to the environment, like reflections and so on and so forth. So I'd say ultra wideband is just much more accurate and much more stable in difficult environments. Yeah.
Okay. Which is better, two-way ranging or TDOA?
I mean, they have plus and minus. It's two-way ranging is simple. It's easy to set up, but it's going to consume more power, and you'd be limited in the number of devices you could have trying to be located at one time in one area, because it involves a lot more exchanges of pulses. So if you're just tracking one or two things, or tracking a few things very occasionally, it could be a good solution. But if, or you weren't worried about power consumption, but if you wanted a long life tag, then yeah, real-time location would be a better solution. But you need a complex system behind that. I mean, that's the downside. So it's horses for courses, as we say in English.
Then which firmware is provided to be out of the box ready to use ISP 3080?
So basically there's a two-way ranging solution. If you buy the development kit, you've got a two-way ranging solution that it really is preloaded even onto the devices, so it'll just work. You just get the devices out. We've done an unboxing video on our website that shows you this, so you can just take it out of the box, and you can see a two-way ranging solution in action. The video on our website shows you this, and I certainly didn't program anything to do that. So you have that example out the box, and yeah, so that's probably the good starting point for using it. Yeah.
Okay. Good. Do you think ultra wideband will become standard in mobile phones?
It's going that way. I mean, the high-end devices have it. You know, Apple's put it on standard on, I think, on pretty much every iPhone. The Samsung top end, you know, the Galaxy S something or others, they seem to have it. Google have put it on their phones, so it's not. I suppose it's not on all of the phones. So the sort of, and it's not just those. There are some others like Xiaomi and Motorola's got it on one. So I guess it tends to be on the higher end devices. But the history is, you know, new features start on the higher end devices and then moves down the range over time, and then hopefully the chip prices go down because they get more volume. And you know, classic. You know, this is how Bluetooth started. It started on new high end devices. And then Bluetooth Low Energy, if you look back to 2010, 2011, 2013, you know, it became, and then it's become absolutely standard now. So it's heading that way, shall we say, but it takes time.
Yeah. Dan, do these modules come with an application, or is that up to the user to develop? It's, I think, for your ultra wideband module, the question.
Well, I'd say we there's the two-way ranging example, which is available in source code, as you know, as well as a preloaded application just to play with it and see how it works. So that's a good starting point, and it obviously comes with the Nordic software as well for Bluetooth, and a sort of driver, if you like, for the UWB. But yeah, your application to do particularly what you want to do, you have to write that because it's obviously got to meet the demands of your particular needs. But there's quite a lot that comes with it, so you're not like starting from zero. But yeah, you have to write obviously an application to tailor it to what you want to do.
Okay. Super, that was also the last questions. Thanks to all. And if you have further questions, like I said before, don't hesitate to contact ourselves, Rutronik, or also Inside SIP. Thanks, Nick, for your presentation today.
You're welcome.
And see you also in our Bluetooth session again in 2 weeks. So yeah, we are at the end. Thanks for all the audience who have joined this webinar, and see you hopefully in the next webinars. So bye.